Okay, today we will see another problem. So let me first tell you what is the problem. The problem is called the selection problem. So what is this? So given a set of numbers, say I take 1, 3, 5, 6, 8, 100, 200, 30, 40, like this, and we are asked find the median of this set of numbers, or in general I can ask you find the kth smallest in this number. So find kth smallest number. Now for k is equal to 1, this is the minimum finding. Suppose let's solve that problem. I know all of you can write an algorithm immediately to find the minimum. So if I write that function mean is equal to 1. So I assume the numbers have been given in an array A. So for I is equal to 2 to n, do if A mean is greater than AI, then mean is equal to I, and if n4, and you output mean is equal to A of mean. So this is a very simple algorithm. So what we are doing is we are seeing the numbers from left to right in the array and always keep track of the index which contains the so far the smallest element, and you output the smallest here. Now how much time does it take this function? Order of exactly how many comparisons? Exactly n minus 1 comparisons. So we have order of n complexity, this algorithm. This is a very simple algorithm. But the problem becomes a little bit non-trivial when we say we are not only interested in the smallest, but also in general the kth smallest. So suppose I ask you not to design a very efficient algorithm or anything like that, but just a naive algorithm. How would you solve this problem? Find the kth smallest. Right. So what you can do, you can sort the array and always scan from the left to, suppose it is in increasing order, you scan from the left to right and find the kth one. So how much time does it take?
N log.
So this will take, so if I sort, by sorting, how much time is it taking? N log n. But suppose somebody is saying my k is small, suppose k is equal to 2, would you sort? For k is equal to 2, you should not sort, because you find the smallest first, delete that element, take the next smallest, and this will take 2n time, order n time, instead of n log n time, which is much better. So suppose what I am saying, instead of sorting, suppose you do this, you first find the first smallest, then find the second smallest. How much time does it take? Order n, so order n together, which is much better than order n log n. Okay. So in general, suppose I generalize this algorithm, what does it do? How can you find the kth smallest? Order k n time. What you do? First take the smallest, delete it, take the smallest, delete it, do it k times. So that will take, so repeated mean finding will give you order of kn time. See, now you cannot say that this is better than this, it all depends how k is. So you cannot guarantee whether this is better or this is better. So what you can see, you can show that we have an algorithm, you can always see what is the value of k and you can choose one of these two. So you can say I have an algorithm order minimum of kn n log n, which is a better way of saying either I do this or do this. Okay. Now this is our solution so far. Let's see how can we solve this problem in linear time. So that is our goal today, to solve the kth smallest in linear time. Before I give you the algorithm, let me first use what we have already done. If you remember in the last lecture, we had a partition routine. Given an array and a pivot, we partition the array into two parts, where the left part has the numbers less than the pivot and the right part has the numbers greater than the pivot, greater than equal. So that routine, can we use that routine to solve this problem? Yes, it turns out that we can do it very easily. So let me write first, and then you will see it immediately how you can solve this. Now I am going to write this as select now, but I will change very soon this algorithm actually a little bit. So I am putting a gap here, I will change the name that time. Now this select has two indices p and r. They are basically the left index and right index of the array, which contains all the numbers from which we have to select the number. And I, this is going to be a recursive algorithm. So in general we are passing the parameter I. What does it mean? It takes the array A, whose left index and right indexes are p and r respectively, and we are going to find the ith smallest in this array from the left. Okay, ith smallest. So that is the parameter we are passing. Now first, if p is equal to r, what should you do? If p is equal to r, then we return basically p. Else what we do, we partition the array. Remember we had the partition routine? I am going to use the same routine. It returns the index where it partitions the array. So q is equal to partition PR. So it will return a index where the array will be partitioned. Now let us see how many numbers are there to the left of q, including q. So that will be what? Q minus p plus 1. So what should you do now? You have this many numbers which you know which are less than the number in q, and you know all the numbers to the right of this index q are all greater than this pivot. So what should you check? You check whether I belongs to the left part or right part. That you can check now easily. You can check whether the index, the ith smallest, whether it belongs to the left part of the partition or the right part of the partition, because you know all the numbers in the left part are less than equal to all the numbers on the right part. So if I is less than equal to k, definitely you know that the ith smallest will be in the, if I is less than equal to k, in the left half, and if I is greater than equal to k, then you know I is in the right half. But you can always give the recursive call with a different parameter. So let me write it down. If I is less than equal to k, then return I am going to give a recursive call, select p q, then what? How should I give the call if I is less equal to k?
I.
I, not k. It should be I, because you are trying to find in the array p to q now the ith smallest element, right? But now you have updated this q here. Instead of p and r, you have updated to pq. Okay. Else, if that is not the case, then return select. What should be the parameters? Q plus 1
R.
R, then
K plus I.
I.
it's not k plus
I.
not I.
I minus K.
I minus k, right? It should be I minus k, because all the numbers in the left half, that is k numbers, they are already less than this number, you know. So you have to find out what is the I plus kth number in the right half. That will be the ith smallest in the original array, right? So what I am saying, but in picture it means this. Suppose this is the k numbers, and you know I belong somewhere here. Ith number belongs somewhere here. So you know all these numbers are less than this number. So you have to find out I minus k number, I minus kth number here, which will be the ith number in the original array, because all these numbers are less than this. That you already know.
Sir, initially when these functions called first time, what is the value of I?
That is the original value of I, which number you are trying to find out. So suppose you are trying to find out, say, fifth element. You call this function select PR5. I have to write the general I because we are going to call it in a recursion. So select q plus 1 r I minus k, and that's it. That's the algorithm. And if yes, okay, so this is the basic algorithm, which is very simple. Now let us analyze this algorithm. How much time can this take? So can somebody tell me how much time does this take? How much time in the worst case this algorithm will take? Yes, very good. It is n square. Why? Because in the worst case, again the partition routine may partition the array in a very bad manner. It may be 1 and n minus 1, and probably you have to search, give the recursive call in the n minus 1th part. And it can happen repeatedly. Remember that tree I drew for the quick sort? The skew tree, all are 1 n minus 1, 1 n minus 1, that way. If it is divided that way all the time or most of the time, from our analysis it is not required that it has to be done all the time, but if it happens most of the time, then also it is bad. So in that case, again our complexity will come Tn is equal to T1 plus Tn minus 1 in the worst case, and that will give rise to a complexity of order of n square, which is already bad, which is worse than n log n. Then why did we take this trouble at all?
Can be done in 2n in most of the time. I mean order n.
Yeah, so that's the point actually. Ultimately, why did we choose this algorithm? That we can make this algorithm a little bit more efficient by using something else, and the tricks already we know a little bit. I am coming to that point. So let me just first write down the worst case complexity of select is order of n square. It happens when partition returns 1 versus n minus 1, 1 versus n minus 2, like this. Now, as he has pointed out, someone has pointed out, most probably this one returns or performs well most of the time. But I told you, to say this statement, you have to be very careful. Then you have to say which distribution you are working on. If it is a random distribution, something, if it is the exponential distribution, something else, something, it all depends on the distribution. You cannot just make that comment, and then you have to analyze it. But we already know a trick where we don't have to care about the input distribution, but still we can say something about the randomness. We introduce the randomness inside the algorithm, inside the data structure. We don't depend on the randomness of the input, and that is already we know that those type of algorithms are called randomized algorithms, and that's what we are going to do. So what the change you will make in this algorithm to make it a randomized select. So that's what, so I will make now random select. So it becomes a random select. What change would you make here? Instead of partition, you call random partition. You remember we had a random partition also. So we just, here we put random partition, and this is random select, this is random select. That's it. Those are the changes, and suddenly you have an randomized algorithm instead of a deterministic algorithm. And let us analyze this algorithm with this randomness. Remember, if you go back to previous lecture, we have seen how this random partition returns the Q randomly. All indices between P and R are equally likely to happen, and that's the key point here. That's the key point here. So let us now analyze this randomized algorithm. So we have now randomized selection. This is by using random partition. Now you have to recall something from previous class. I told you in the partition routine there are two cases where it partitions into 1 and n minus 1. When k is equal to 1, that is the pivot is the smallest element, then it happens that the partition will be 1 versus n minus 1. If the pivot is the second smallest element, that time also it happens that the partition is 1 versus n minus 1. For all other k, it is third element, fourth element, it will be k elements and n minus k elements. Alright. So we have to take care these two cases differently. So you recall with probability, so what is the probability that 1 versus n minus 1 happens? There are n possibilities, 2 are like that. So 2 over n. So recall with probability 2 over n, the array is split in 1 to n minus 1. And for all other k, which is n minus 1, with probability one over n, it is split k to n minus k. Okay, because all others are equally likely to happen. So their probability is 1 over n. And since this is happening twice, that's why it is 1 over n plus 1 over n, 2 over n, the probability. Alright, actually for analysis this does not matter a much. You can forget about this 2 over n business. But let us be as precise as we can be here. You don't have, actually the most important part is this, that for general k between 2 to n minus 1, it is splitting k n minus k with probability 1 over n. That is the most important thing to remember. Okay. Now we know the probability with which the partitions are happening. Now, if we have to analyze this algorithm which I just told you, the random select, suppose I want to write Tn, and suppose it has split into k and n minus k. How much time does it take? How do you express that one? Tn is equal to, just 1 minute. So you are saying Tn will express as Tk plus Tn minus k plus order of n. But go back to the algorithm. Should it be Tk plus Tn minus k? Are we giving two calls? Either of the two. See, if you do Tk plus Tn minus k, it becomes a quicksort. But here we are not giving two calls simultaneously. One of the two. That's most important here. That is the key point here. That's the difference between the quicksort and this algorithm. Quicksort, our randomized analysis gave n log n. Remember that? So if I write Tk plus Tn minus k, I cannot beat that. But I am saying I will be giving you a linear time algorithm. What is the difference? Somewhere it must make a difference. The difference is here. We are not giving two calls, only one call. So how do you express that? You don't know which one is going to be called. Let us take the maximum one. Max of Tk and Tn minus k. And it will be determined by the value of k, whether k is greater or n minus k is greater. So I can express now. So I am writing Tn is equal to, and remember this k business can happen with a probability of 1 over n. So I can sum over all this k and then take 1 over n to express this complexity. Just like a quicksort we did. So Tn is equal to 1 over n. Now let me write this particular case a little bit differently. Max of 1 n minus 1. This is a particular case, two cases. Plus sigma k is equal to 1 to n minus 1 T of max k n minus k, and this plus order of n. This is our total complexity. This order 1 over n is over this entire thing.
So 1 and n minus 1.
Yes, just to be uniform. Yeah, I know that 1 n minus 1 most of the time is more, but when n is equal to 2, that's also 1. It's fine. Let us just write it. This is less than equal to. Actually, you cannot write it n minus without max, because suppose n is equal to 1, n minus 1 is 0, but you have to spend t1. So to be precise, you have to write it. Okay, so 1 over n, this I am going to write t n minus 1 as you have pointed out. N minus 1 is going to be greater than equal to 1, because when n is small, I can always express this one as some constant. T of some 1 is some constant. I am not bothered about that analysis. I always know T of 1 is some constant. If you have only 1 or 4 elements, you can always do a brute force method to find the smallest or kth smallest. So I am replacing this, and it is always less than equal to I am doing. Plus, can you tell me whether I write this? Let me write it. Then you tell me whether I am wrong All right. And if I am right, why am I right? Can you tell me how can I write this like this?
Maximum is always going to be n minus k for first and by 2.
Right. Between k and n minus k, maximum is always within n over 2 seal and n minus 1. Is the upper half. So I can always take that and I put 2 because left half which is from k is equal to 1 to n over 2 minus 1, that I am approximating with always the upper part. So that's why this left part of this and the right part of this, when I say left and right of this equation, we are splitting it into this, around this number. So expressing this with a factor of 2, and that's why it is tk with a factor of 2. It is less than equal to, I can always do that, taking always the maximum. Yes.
So, when we take k equal to 1, max 1 and n minus 1 is covered in that.
Max 1 and n minus 1 is covered.
When k is 1.
When k is 1, because k is 1 is basically nothing.
So then, why write it again?
I'm just writing this max 1 and n minus 1 is that t n is equal to 1. What do you mean by writing again? I have to write this expression here to make it simplified.
In the first statement, there we are taking k is equal to 1 to n minus. We take it k is equal to 2.
I see. So you are objecting here, it should be from 2.
Yes, sir.
Your objection is from k is equal to 2. Yes, let us write it as k is equal to 2. But since less than equal to, it does not matter. I can include it also.
But we have,
Let us be uniform, that's why.
We have 2 partitions.
so for 2 cases, we have 1 and n minus 1.
Yes, we have taken 2 cases here, max of. See, it's the order business which is important. Whether I put 2 here, it does not matter. So I can put 2 here, it doesn't matter. And k actually, yes, that's why another reason was k is equal to 1 here. But if you object, what you can do, max 1 n plus minus 1, put another t max 1 n minus 1. It will not matter. Okay, and take from k is equal to 2 to n minus 1. That will be absorbed. But as he has pointed out, one of t max 1 n minus 1, I can absorb it here.
But sir, that term we will get when we put
The last one.
k is equal to n minus 1. When we put that term will get.
Right. That term will be. But if you take k is equal to 1 to n minus 1, you are and 1 here, you are covering everything.
But sir, if we write it from k is equal to 1 to n minus 1, there will be 3 terms containing 1 and n minus 1.
Okay. Suppose if you object into that, put k is equal to 2 to n minus 1, put another t max 1 n minus 1. It does not matter. It will not affect your analysis. It will not affect your analysis. Alright? It will not affect your analysis. You will see. Because if you put another t max 1 n minus 1, what is t n minus 1 I am going to replace with? On. T n minus 1 will be on square. And this on square will give you on. So suppose you have one on, another on, that will be absorbed in this way. See, it doesn't matter. Okay, so let us be uniform. K is equal to 1 to n minus 1. Otherwise, you have to every time you have to take care of 2 to n minus 1. That's very clumsy for the analysis. See, while analyzing, you should try to simplify as much as possible because your analysis is going to be anyway a little bit clumsy. But if you know that it is not going to affect your final analysis, something you can do, you should be doing it to simplify your analysis, and that's what we are doing. Okay, so this we know order of n square. So this will be order of n square 1 over n. That will give you order of n. That will be absorbed here. So I can forget this stuff. So I can write less than equal to 2 over n sigma k is equal to n over 2 n minus 1 tk plus order of. Agreed? Now let us see. Now comes the same trick as we did for quick sort. So we'll how to prove this? I want to prove it to be a order n. I know it is going to be order n. So we can use induction. So let's see. So we will assume Tn is less than equal to C times n for some large constant C greater than 0. All right, Tn is less than equal to Cn. Okay, now when induction I mean for, so it will be inducting on some value of k, Tk. For k less than n, this is true. I have to prove that k is equal to n, it is true. If you remember the induction, for k less than n, it is true. So I can assume Tk is equal to C times k when k is less than n. Then I have to prove that Tn is less than equal to Cn. That will be enough for our induction. And now, of course, for base case, I am not going to the base case. That's obvious. T1 is constant. Yes, please.
Plus some constant Cn plus.
I'm not assuming plus some constant. This is sufficient for my induction. If you want, you can, but I am not assuming. See, that time I had to assume for something else, but here this will be sufficient for my induction.
How can we know that when to use it?
No, I told you there is no. I cannot give you a formula. So this is just try. So what you should do, you should try Cn. Suppose you cannot, try hard for your induction to go through. Don't give up immediately. If it is not working, so I should assume something else. Probably you are not doing it properly. So give some effort on that. Suppose you are convinced that this way it is not going to work, try something else. Cn plus B. Okay. But how do you know that this is going to be a linear time most of the time? That I know. And that is the experience. Once you go over this algorithm course, you will develop. You should develop that Q. That how do you know what is the complexity of an algorithm roughly? Here I know it is going to be linear because of that fact. I am not going to recurse on the two parts. I already know that I am not going to recurse on the two parts. I am going to eliminate one of the part. And if the division is proper, what we are eliminating? We are eliminating a fraction of the input. And I will show you very soon that if you can do an algorithm which can eliminate a fraction of the input all the time, it's going to be linear. So that fact we know. So that's why I can assume. Okay, so let us now induct. So I have to prove Tn is less than equal to Cn. Now I know by induction Tn is less than equal to, so Tk I put Ck basically. So if I put Ck, what do we get? 2Ca over n, then sigma k is equal to n over 2 n minus 1 k, right? Plus order of n, right? You agree? Now this is less than equal to, or I can write this as 2c over n sigma k is equal to 1 to n minus 1 k minus k is equal to 1 to n over 2. This is just to get the right bound. I added something here, subtracted it. Yes. So this is less than equal to Cn minus 1, because this will give you what? N times n minus 1 over 2. That will cancel. N over 2 over n will cancel. So this will give C times n minus 1. And this will be what? I can roughly assume it as n over 2. So it will be n over 2 times n over 2 minus 1 over 2. So if you do that calculation, it will give you C over 2 n over 2 minus 1 plus order n. Now this is less than equal to C4 Cn plus order of n. Okay. Now remember, I have to prove it is less than equal to Cn. I have C4 Cn already here. So 1/4 of Cn is still left with me, which I can play the trick with the constant. See, order of n is basically some constant. You will choose some constant. So I will use C. I will choose C such that that constant become less than equal to 1/4 of C. You see the trick. You see the point here. Yes. So order of n is what? Actually it is say some C1 times n I can write. So I can always write this one less than equal to 3/4 Cn plus C1 n for some constant. So now I am saying now choose C is less than equal to 1/4 C1. I can choose that. C1 is a constant, I can choose C. So if you do that, this is less than equal to Cn. To carry the induction, because basically I have to do this, that's why this split and all these things we did. Yes.
In the beginning, we assumed that Tn is less than or equal to Cn for some large constant C.
Right. I didn't choose that time C. Just 1 minute. So you want right. Right. You're right. C1 is less than equal to 1/4 C. So see, I said I'll choose the C later. When I say it later in the analysis, I will see what is this, what do I require to choose. Okay, now I know that C1 must be less than equal to 1/4 C. So C should be greater than equal to 4 C1. Okay, so now I can go back to my analysis. I already know what is C1 here, because that is coming from your some constant that you must have chosen somewhere. That analysis is coming from the partition routine that you can always choose. So you choose your C1 here. At the beginning, since I did a forward analysis, I know what should I choose. I just take 4 times C1 and I'll tell you what, choose this C, then carry out the induction. I know the induction will work now. I chose it in a backward manner because I had to see in future, then I chose it. Then suppose I don't tell you how did I choose. At this point you come to me and I tell you, okay, choose this C. I know it will work because I have calculated a little bit in future. All right. So this is the analysis. Actually, this is what we already did in quicksort analysis also. Randomized quicksort. We did the same thing. We chose the constant later after doing the forward analysis.
Sir,
Yes.
in the quick sort, we choose Tn is smaller than equal to a n log n plus some constant.
Right.
There, if we choose Tn is smaller than equal to Cn.
You cannot. In quicksort, you cannot choose Tn is equal to less than equal to Cn. Your induction will not work because Tn actually is more than Cn. How can you make your induction work? Your induction will only work if something is correct. If your assumption is correct.
So, but the equation Tn equal to 2 by n sigma k is equal to 1 to n minus 1.
Right.
Here also this similar, something like.
It cannot be similar. There was something else. There was k log k. There was a k log k business. Somewhere. Your analysis, these two analysis is a little bit different. Go back to your analysis and see it. Quicksort and this analysis is not exactly same, but the line of attack is same. It was k log k there. Here there is no log term coming.
But Tn is smaller than equal to 2 by n into sigma k of k equal to 1 to n minus 1 tk plus 4n.
Let me go back. See, yes, there was a 2 times. That's the problem. Q is equal to 1 to n minus 1 tq plus tn minus q. There are 2 terms. Here there is only 1 term. There are 2 terms and here is only 1 term. And ultimately you simplify, there is k log k is coming when you simplify. See that the difference, your expression Tn in quicksort and expression in Tn here are not same. There was sigma q is equal to 1 to n minus 1 tq, and here tq plus tn minus q, here is only tq. That's the difference, and that's what the difference in the algorithm. You are not giving 2 calls, only 1 call, and that is making all the difference. So in the next lecture, let us stop the randomized quicksort here. In the next lecture, what I will show you how to design an algorithm which will find in a deterministic manner. So we will not have on an average case analysis, but we will have even in the worst case, it will run in linear time. So these analysis has shown that the randomized selection returns you the k smallest in average time of linear time complexity. So order n complexity, but that is the average case analysis. But in the next one, we will show in the deterministic algorithm, it will return the k smallest in worst case linear time.